Hello, welcome back. The title of this lesson is called Naming Acids, but really it's an introduction to what an acid is along with the idea of naming acids, all right? So in the previous lessons, we've learned how to name ionic compounds, so here we transition to naming acids. Before we do anything else, we have to talk about what is an acid. First of all, you have experience with acids every single day, but you may not be aware of the chemical definition of what an acid really is. They're a very important broad class of compounds, right? And so everyday experience, if you bite into a lemon is acidic, right? We even say that in everyday language. It is an acid. But what does that mean? Another example, vinegar. Vinegar is acidic. You notice in both of those cases a very pungent, kind of sharp taste to it, okay? Now there are other acids, of course, that we can't eat, or you shouldn't eat, and the most famous of which is your stomach acid, hydrochloric acid. You may have heard of that term, hydrochloric acid. It's stomach acid. Now there are other acids, and the image that we put in our mind when we think of an acid is we think of like something that can eat away at something else, right? And we're going to learn as we go forward why acids are reactive or can be reactive like that. Why can acids, quote unquote, eat through things? Now they're not really eating through anything. They don't have a little mouth, okay? But what it means is when you have a strong acid, it can be very reactive. And we're going to learn why that is. And when something's very reactive, it can eat through, quote unquote, metals or other things, but it's eating through it just because it's very highly reactive and it's having a chemical reaction with that substance, which is changing it into something else. So you think of acids eating through something, what's happening is a chemical reaction with the acid to produce some other kind of product, okay? So we're getting a little bit ahead of ourselves, and actually we're going to have an entire sequence of lessons in much more detail with acids. So we're going to learn what it is here, but we have, just so you know, in the back of your mind, an entire set of lessons that deal with all of the details involving acids. So there is a basic definition of an acid I'm going to share with you today, but just keep in mind that as we learn more about acids, the definitions, we're going to refine them and tighten them up a little more. An acid, for the purpose of this place in the class, at this stage of our learning, an acid is a substance which yields hydrogen ions when it's dissolved in water. I'm going to say that again, and if you could lock it away in your brain, I recommend you do that because it's going to be a useful definition as we go forward. An acid is just a substance that when you dissolve it in water, it yields hydrogen ions. Now hydrogen is way up here, element number 1 on the periodic table. So hydrogen is literally the simplest atom we know about. Hydrogen is a single proton with a single electron cloud around there. Single electron, single proton. So when I say hydrogen ion, I'm talking about a hydrogen that has lost its electron, a positive hydrogen ion. So a hydrogen ion is another way of saying a proton, right? So they don't say it that way, but I could have written the definition. Acids are substances which yield protons in solution with water. We're going to talk a whole lot more about a better definition for acids and the cousin of an acid, which is called a base, which we're going to talk about later, the opposite of an acid, which we call a base. But for right now, I want you to think of it as something that when you dissolve it in water, it makes these hydrogen ions, which are just hydrogen atoms which have lost an electron, aka a proton, all right? Now that definition is so important for us to keep in our mind before we name anything that I am going to write it down, and it's very simple. I'm going to say it's an acid is a substance, I don't have to write the word substance, which yields hydrogen ions. I'm going to write that as H+, because hydrogen, when it loses an electron, is just a hydrogen nucleus with a single positive charge, which is the same thing as a proton, right? Hydrogen, H+ ions, when dissolved in water. In water, right? Now, when you construct an acid and you put it together and you write down the chemical formula, you, in general, you always write the hydrogen first in the formula. So for instance, I'll give you a couple of examples. Hydrochloric acid, we're going to learn exactly why it's named the way it is, but it's H. H comes first with chlorine, Cl. That's hydrochloric acid. Another acid, H2 SO4. We're going to learn how to name this acid here in a little bit. But notice that the hydrogen is listed first, and then the rest of whatever it is comes second. The hydrogen is listed first, and then the rest of whatever it is you have there is listed second. Now, both of these substances, if you were to dissolve them in water, will yield hydrogen ions. Why? If you think about table salt's totally different. Table salt's not an acid. But you know that table salt is a compound that consists of 1 atom of sodium in a ratio to 1 atom of chlorine. But they're ions. When salt is a crystal sitting on the table, it's not in any water, it is bound up in a repeated 3D structure of sodium, chlorine, sodium, chlorine, sodium. It's 1-to-1 ratio, but they're ions because the sodium has lost an electron and the chlorine's gained an electron, and opposites attract, and they're in the solid state like this. Then if you dissolve that substance in water, then the water is able to dissolve or break down the sodium ion, which remember are ions, and the chlorine or the chlorides, which are ions. So the water literally rips apart at the microscopic level the atoms which are in the crystal lattice of sodium chloride. And so what you have in water, if you could put on special goggles and look at everything floating around, the atoms, you would not see sodium neutral atoms and chlorine neutral atoms. You would see sodium ions floating around, positive ions, and chlorine ions floating around. They would bump into each other and bounce off the walls, but they would be ions, okay? So because this has a charge and this has a charge and they were bonded together ionically, when you put them in water, water rips it apart. By the way, why does water dissolve things? Why is water a good solvent, we call it? We learned before that water is polar. I don't want to rehash the whole lesson, but water is a bent molecule, right? And so the oxygen is very slightly, the oxygen is very slightly negative. It pulls the electrons a little bit closer to it, and the hydrogens are very slightly positive. So because water is a little bit, half of it's a little bit positive and half of it's a little bit negative, and you have trillions of them floating around each, where half of the water molecule is positive and the other half's negative, then when you dump sodium chloride in, what happens is the sodium is going to be attracted to the oxygen because opposites attract. Sodium's positive, the oxygen on the water is slightly negative, and it pulls on it, right? And the opposite is happening with the chlorine. The chlorine's negative, but the hydrogen in the water is positive. And so it's pulling on the other side. So the sodium chloride is bound together. As soon as you put it in water, the water molecules are literally ripping it apart from both sides because one half of the water is pulling one side and the other half of another water molecule pulling the other side, and it overcomes the sodium chloride ionic bond and it pulls it apart. So then you have the sodiums floating around, ions, and the chlorines floating around. So that's enough about salt. How does this apply to acids? Because in here, if you had such a thing as a solid hydrogen chloride, basically, and dissolved it in water, it's going to rip it apart. And even though hydrogen is a little bit weird in that sometimes it can gain and sometimes it can lose electrons, in this case, when it's connected to chlorine like this, it's behaving as a positive ion. The chlorine is behaving as a -1 ion. You put it in water, it gets ripped apart just like sodium chloride. This thing gets ripped apart too. So whenever you put this in water, you have hydrogen ions floating around. And you also have chlorine ions also floating around. And here you would have hydrogen ions floating around as well. So the definition, an acid yields hydrogen ions when dissolved in water. Where do the hydrogen ions come from? In this case, the hydrogen ions come exactly from what you have just dissolved in water. In the back of your mind, just know that a hydrogen ion is a proton. So that proton is just hanging out in solution. And so why can acids be stronger? Well, the more, I'm getting a little ahead of myself, okay? I'm not trying to do a whole lesson in acids, but the more hydrogen ions you have dissolved in the water, the stronger the acid. Think about salt. The more salt you dump in there, the more salty it tastes. You could think of it being a stronger salt, stronger dissolved salt. Very, very, very weird tasting if you put too much salt in the water, okay? If you have a lot of this acid dissolved in there and a lot of hydrogen ions, then you have a bunch of protons floating around in your water, and then it can react with other things. When you pour the acid on a piece of metal or something, it can react with it because you have a lot of free hydrogen ions, which can be very reactive, okay? So that's kind of getting a little bit ahead, just more of a preview and motivation to whet your appetite where we're going. In this lesson, we're mostly concerned with identifying acids and naming them. So let me show you how we're going to name them. Once we actually learn how to name them, then it's pretty easy, actually. It's not a difficult process. But what we have to do is take a few different examples. Let's take a look at our famous hydrochloric acid, HCl. This is hydrochloric acid. All right. How do we name this guy? Basically, it always is named based on the negative ion, the anion here. So in this case, hydrogen is paired up with chlorine, which in terms of its ion is chloride. So basically, the ion here is chloride. So another way to look at this, instead of calling it hydrochloric acid, you could call it hydrogen chloride. We never call it that. We call it hydrochloric acid, but this is a chloride ion. All right? Now what you do is when it's hydrogen with a simple IDE ion, then what you do is you take the IDE, I'm underlining the IDE, and you turn it into ic. And then you add the word acid. And you put the word hydro in front. So hydro comes in front. And because chlorine has an IDE, it turns into an IC, chloric. And then you add the word acid. All right. So when you have hydrogen with a simple negative ion, anion, that is like a chlorine or a bromine or a fluorine or something like this that has an IDE ion, you just change the IDE into an IC. So notice that chloride becomes chloric. Chloric, so hydrochloric, and you put the word hydro in front, chloric, and then acid. All right, now we're going to get some practice with that, so don't stress out if it doesn't make a ton of sense. But what I'm going to do is I'm going to write down a few different prototypes of different kinds of acids, and we're going to refer to them as we do our problems. Because once you have a prototype in your mind, you can solve any of these problems. So the first prototype is when you have hydrogen and a simple negative ion, which is named in terms of IDE, just like we name all the negative ions on the periodic table over there. All right, now let's take another acid, H2SO4. Now this is different because the negative ion is not just an element like chlorine was, it's SO4. Now, all of the acids are named in terms of the negative ion. So and this is not, in this case it was IDE, chloride, but this is not an IDE ion. What ion is it? What is SO4? SO4 is sulfate. So this acid is going to be named from the root of the anion, sulfate, right? Whereas before, the anion was chloride, and so we named it this way. Here the anion was sulfate. So it has to have something to do with sulfate. And what's going to happen is if the anion ends in ADE or ATE, then we change that to IC. But we don't put hydro in front. We just literally name it based on the ion here. And so what is it? It's sulfuric acid. And so this is sulfuric acid, H2SO4, very famous acid you may have heard about in the past. So again, how is it named? It's always named based on the negative ion. In this case, the negative ion was chloride. So when you have a IDE ion, you change it to IC, you put hydro in front, IC acid, hydrochloric acid. It's going to be hydrochloric acid, hydrobromic acid, hydroiodic acid, if it was iodine right there, because all of those would be the IDE ion. In this case, this is a sulfate ion. So you don't do hydro anything, it's just named based on the ion. This becomes ic, sulfuric acid. That's how we name that. And there's one more prototype I need to give you before we can solve our problems, and that would be an acid that's less common, that you probably may not have heard of, HClO2. This is just a prototype, so we can get our problems done. So obviously this is not an IDE ion, and I don't recognize what it is. So what is ClO2? So ClO2 is chlorite. So we have the ATE because we just did one based on sulfate. Now we have to name it based on ITE, which is, in this case, chlorite. So let me write down the ion. The ion name is chlorite. Right? So I'm going to underline the last few letters. The ITE becomes OUS. And again, you don't do hydro anything. It's just named based on the ion. Chlorus is what you name it. So chlorus acid. Chlorus acid. Again, not as common, not something you may have heard of, but this is how you name it. With these pieces of information, we can name acids. So all we have to do for every problem is just identify what category we're in, and we just follow the rules. After a while, you're going to find out that you pretty much come in contact with the same acids over and over again in most chemistry problems, and so it won't be so difficult. But knowing how to name them broadens your horizon to encountering and understanding other things. So from the top, we're going to do a lot of problems, but from the top, if the anion is an IDE, like a chloride, iodide, fluoride, bromide, things like this, then it's hydro something ic acid. That's basically it. Hydro, whatever it is, ic, change it to ic acid, right? That's your prototype for that. If the ion is instead an ATE, like a sulfate or a nitrate, then all you don't do hydro anything. It's just sul. This turns into an ic, so sulfuric acid. Another example would be nitric acid. We're going to write down nitric acid in just a second. That's another very common acid. And then the other category is if your ion is ITE, you change the suffix to OUS. Again, you don't do hydro anything. It's just named on the ion. Chlorous acid. So chlorous acid, hypochlorous acid, things like that. So it just basically goes on what anion you have and what the suffix is. You change it and you name it. That's it. So let's go over here to problem number 1. Let's say that I give you HBr, and I want you to name this guy as an acid. First of all, is it an acid? Well, you have a H, which from the periodic table, again, hydrogen can do either thing, but it's going to want to lose an electron here. And because bromine is going to want to gain an electron. Bromine's here, it's going to want to gain an electron. So to have any kind of attraction or anything, then hydrogen is going to want to lose the electron. It's going to want to give that electron over to bromine, and then they're going to become partners and be attracted to each other. So you have an acid here. If you dissolve this in water, then you're going to get these hydrogen ions because it lost its electron, gave it to the bromine, and the H plus is going to be floating around inside your water. The more H plus hydrogen ions you have, the stronger the acid. So when we have a really strong acid that can melt through whatever, steel or something, then it has more hydrogen ions. And there's a way to measure how strong an acid is. We're going to talk about it later. It's called the pH scale. And we're going to learn about that. But I'll tell you right now, the pH scale is going to essentially measure how many hydrogen ions you have. The more you have, the stronger the acid. Simple, right? So how do we name this guy? Well, what category are we in? The ion here is not chlorine, it's Br, which is bromide, right? So it goes as bromide. The anion is bromide, right? And because it has an IDE ending, we just change that to ic. And because it's an IDE, the prototype says we put hydro in front, whatever, ic acid. So we call this thing hydro bromic, whoops, not 2 words, bromic acid. If I can spell acid correctly, sorry about that. Right, that's it, hydrobromic acid. A lot of talking just to get to hydrobromic acid. All right, let's take a look at problem number 2. Let's take a look at HBrO3. Now this looks very similar to this, but it's obviously not the same because yes, you have hydrogen, and so you suspect that this is an acid, but it's not a simple anion or bromine. There's BrO3. Let's see, is there a polyatomic ion with BrO3? And we see right here, BrO3 is a polyatomic ion. It's called bromate. Bromate. So the negative ion, you just write it down, you say bromate. Right? And now you're no longer in that first category. Because it's bromate, you're no longer up here. It's not an IDE ending at all. It's ATE, it's this one. So just like sulfate turned into ic, sulfuric acid, this is going to turn into bromic acid because it's going to go and change into ic. So bromic acid. Right? Just like it was sulfuric acid based on the sulfate, this is bromic acid based on the bromate. All right? Next problem. Let's say we have H3PO4. Again, the acid is always determined based on its anion, which in this case is PO4. So what is that? It's got to be some kind of polyatomic ion. What is PO4? PO4 is a polyatomic ion called phosphate. So that's the anion. It's phosphate. And what do we do for 8 up here? We just changed it to ic, and bromate was bromic acid, so phosphate will be phosphic acid. Except phosphic acid sounds weird, so we actually put phosphoric acid. And that's the final answer. These little weird changes, you would think it would be phosphic acid, right? But it's really phosphoric acid. These little slight exceptions is just stuff you'll pick up over time. Now, before I go any farther, I do have more problems, but I don't want to get too far ahead before I show you that these things, in order to make the acid, the thing is dissolved in water, okay? But you can still do the crisscross to predict the subscripts on everything, all right? So we're writing these things as if they are solids here, but the definition of the acid is a substance that yields H+ ions when dissolved in water. Acids are almost always dissolved in water, okay? You could have hydrogen chloride just bound up in a lattice, but you don't usually see that. You see it dissolved in water, and so everything's floating around and the acid's in a liquid phase. But in order to write these things, if I just told you it was hydrobromic acid, you could reconstruct this, because what you would do is you would say, all right, the hydro part means hydrogen, the bromic means Br, and from the periodic table, I can see that the hydrogen is going to want to lose 1 electron, and the bromine is going to want to gain 1 electron right here. And so from the crisscross, you can see it's going to be HBr, and that's a check mark on that. Now, what about this one, HBrO3? So if I give you bromic acid, or if I give you the ions here, you can say, well, bromic corresponds to bromate, because ic turns into 8, right? So you can say, you got to have a hydrogen in there somewhere, and the bromic is going to turn into a bromate. Again, 8 goes with ic, like this. So bromate, you can go look over there and recognize that it's BrO3, and you'll have to look at your table of polyatomic ions to recognize or to know that it has an overall -1 charge. But once you know that it has a -1 charge, and hydrogen is always going to want to take a positive charge, losing an electron, giving it, you can think of it as giving it over here, then when you do the crisscross, you're going to have HBrO3, which is exactly what we have here. Same thing over here. You have the phosphoric, ic turns into 8, so it's a phosphate ion. So it's a phosphate ion with a charge of -3. So if this has a charge of -3, it's going to give you a subscript of 3. Hydrogen's a 1, it gives you a charge of 1, and that's why you end up with this one. I want to show you one more before I wrap it up. Let's talk about the sulfuric acid, right? How would you write that if you didn't really know? Well, if I just told you it was sulfuric acid, you know what ic goes with 8, so it's a sulfate ion. So you would say hydrogen goes right here, and the sulfate ion is SO4 with a charge of -2. You get that straight from the table of polyatomic ions. Hydrogen is going to want to take a +1 charge, and when you do this, you get H2, the 2 coming from here, SO4, the 1 coming from here. So basically, I guess I'm trying to tell you that these acids, in order to figure out what the formula is, if you're given the name, it functions the same way as ionic compounds. Even though it isn't really used in nature in an ionic solid, like in a lattice, like table salt. I mean, usually acids are almost always dissolved because you need the hydrogen ions floating around to do something useful, to participate in the chemistry. But from the point of view of what is the ratio of these things in the formula unit, you do it the same way. You reverse engineer the name. You say 8 sulfate or sulfuric acid, ic goes with 8, so it's a sulfate ion. You know hydrogen always takes a plus. You know what the ion is, you do the crisscross, right? If you have an us acid, chlorus acid, you know us goes with ite, so you look up the chlorite ion, you write it down, and you do the crisscross, same as before. So we'll do more problems, but I just wanted to let you know ahead of time that not only are we naming things, but I'm trying to show you how you would get these to begin with, or how you would reverse engineer a name. So we only have, I think, 2 more of these actually, or maybe 3 more. Yeah, there's three more of them. Now, instead of writing these down in this way, I'm going to give you the name hypochlorous acid. So that was a good segue, because here we're going to reverse engineer the name and we're going to write down what is the formula for this acid. So first of all, it's hypochlorous. So you look at it, it's not a hydro anything acid, so we know it's not like hydrochloric acid. So chlorous, what is the prototype here? So it's an OUS, which turns into an ite. So the anion has to be hypochlorite. Hypochlorite. How did we know that? Because the OUS is associated with ITE, so hypochlorite. So what is the polyatomic ion? Hypochlorite. Hypochlorite is ClO with a -1 charge. So ClO with a -1 charge on the whole polyatomic ion, and we know all acids have to have hydrogen written first with a +1 charge. And so then once we do the crisscross, we say HClO. The one goes here and the one goes here, and we have HClO, and this is the final answer. Hypochlorous acid, because this is a chlorite ion, and chlorite, ite, goes with us, so hypochlorous. The hypo comes from the name of the polyatomic ion. All right, let's take a look. I think I have room over here. 2 more. Let's reverse engineer this one. Iodic acid. Now your first instinct is that this might be HI, but HI, think about hydrochloric acid. If it were HI, it would be hydroiodic acid, because ide would become it and would be hydro something acid. But there's no hydro anything here. So this cannot be HI, because HI would be, or HBr would be hydrobromic acid. HF would be hydrofluoric acid. HCl is hydrochloric acid. HI would be hydroiodic acid, but it's not written that way. So this cannot be HI, because that's the first thing you probably think of. This has got to be just iodine, HI. But then you look in your table of polyatomic ions, and it turns out that there's actually an ion called iodate. And that is what is going here. So the ion here is iodate. And iodate, and how do we know it's iodate, by the way? Because we have an ick right here. So sulfuric acid, we had an ick, goes to an ate, and it was sulfate. So that's why it's iodate, because what we had is ick. So we know that ick is so many little tongue twister things, but we know that ick goes to ate. So we look for a polyatomic ion, iodate. Iodate. And let's just double check. It was iodate. IO3 with a -1 charge. So IO3 with a -1 charge, and we always have to have hydrogen, which has a plus charge because it just loses the electron. And then we do the crisscross, and the hydrogen gets a subscript of 1, and the IO3 also gets a subscript of 1, and so we have H. Let me just double check. HIO3, and this is the final answer. All right, we have only one more. Sulfuric acid. Sorry, not sulfuric. Sulfurous acid. Sulfuric acid is, we already looked at that one a minute ago, and that's a very common acid. Sulfuric acid is very common, but we don't have that. We have sulfurous acid. We have an OUS. So the OUS must go to an ITE. The suffix OUS goes to ITE. So what's this going to look like? It's going to be sulfite. Literally just replace this. Now it's a little bit weird, right? Because it looks like it would be sulfurous, would change the OUS to ITE. It would be sulfurite. But there is no polyatomic ion called sulfurite. Sulfite is what's there. So there's a very slight, I mean, these are rules of thumb that I'm telling you, but if you literally replace OUS with ITE, you would get sulfurite. That's not a thing. So sulfite is what you're looking for here, sulfite. Now sulfite, as far as an ion, is SO3 with a -2 charge. SO3 with a -2 charge, and then we have hydrogen, which always has a positive charge, and we do the crisscross, so we get H2, 2 coming from here, and then we have SO3, the 1 going here, so we don't need any parentheses. So we have H2SO3. So in this lesson, we introduced the concept of an acid. I actually talked at more length than I thought I would about what an acid is and kind of like even strength of acid, a little bit of a background so you know what we're talking about. And then we introduce the naming convention. Basically, an acid is a substance so that when you dissolve it in water, you get these hydrogen ions, which is just another way of saying protons. Protons floating around your water. I know it sounds weird, but that's a common thing. When you bite into lemon juice, that's what you're tasting. That's what that is. Little protons just swimming around in the water, bouncing off things and reacting and so on, okay? So just like salt, sodium chloride, when you dissolve it in water, breaks up into sodium ions, positive, and chlorine negative ions, negative, and they're just floating around as ions dissolved in the water. If you had a solid sodium chloride and dissolved in water, it would break apart into hydrogen ions and chloride ions floating around. The more hydrogen ions you have, the higher the concentration of them, then the stronger the acid, because the more it can react with things when you dump it on there or you immerse it in there. And so then we have three main classes. You're going to have hydrogen connected to a simple IDE, an element of the periodic table, in other words, on the right-hand side, which are IDE ions. And you name it hydro blah blah ic acid, hydrochloric acid, hydrofluoric acid, hydrobromic acid, hydroiodic acid for iodine. That's how you name those, okay? And then you have where the anion is an ATE, so sulfate. It turns into an ic, and you don't do a hydro anything, it's just named based on the ion, sulfuric acid. Now again, sulfate, if you just put ic here, it would be like sulfic acid. So it's a little bit not bulletproof, because if you do a straight substitution, it doesn't give you exactly what you have here, but you're just gonna have to like understand that these rules are not, it's not a computer program, okay? You have to interpolate a little bit. So sulfate becomes sulfuric, right? And then you have ITE ions, and those ITE turns into OUS. So chlorite turns into chlorus, for instance, acid. And then we did a bunch of examples to show you of different cases of that. So I'd like you to solve these yourself. Make sure you understand the general idea, and then follow me on to the next lesson. We'll do part 2 and get more practice with naming acids.